Okay, here in section 9.2, we're really going to tackle this main idea of Calculus BC concerning a topic called infinite series, and then of course maybe the convergence of something called an infinite series. Just to kind of remind you, 9.1 talked about sequences, and I hope you took note that that really was just a stepping stone or some sort of foundational section to kind of get us ready for this main topic called infinite series. What you should have taken away from 9.1 is just a few of the examples I kind of went over that I asked you to kind of note for future reference, and just some of the basic ideas of sequences that are now going to help us really do what matters in this chapter, and that is look at infinite series. So really look at this section, 9.2, being the proper beginning to this chapter 9. Okay, so before we kind of jump into this idea of an infinite series, let's just kind of start off with a basic little idea, and it's this challenge here. Can you add up all the numbers from 1 to 100 without a calculator? And I guess if you want to pause here and see if you can attempt to maybe figure this out, you definitely can try to do that. But if you don't want to, you can kind of see the approach that we would need to take to do something like this. It would be possible to, of course, add up all the numbers from 1 to 100 without a calculator, but that would certainly be very tedious. So I went ahead and listed off some of the numbers from 1 to 100. I listed off 1 plus 2 plus 3 plus 4, and then 49, 50, 51, 52, and then the last 4 digits. And again, we're adding these all up. This is again helping us build up to this idea of a series, which is the same idea of just adding up a certain amount of items. So there's a little, I guess, trick we can notice here. If we were to take the very first and last terms in this series and add them up, we'd get 101. If we were to take the second term and the second to the last term and add them up, we'd get 101. And if we kind of continue that pattern where we're adding up something at the end that corresponds with something at the beginning, we'll keep getting 101. So you'll notice we just have a bunch of pairs of 101. We have 50 pairs of two things that add up to be 101. So of course we could just simply do some multiplication here to figure out that 50 pairs of 101, or 50 times 101, would be 5,050. So just a kind of interesting way to kind of start off this idea of looking at a series, which is again just another way of saying we're adding up a bunch of things. So what about this series here? What if we wanted to add 1 plus negative 1 plus 1 plus negative 1 plus 1, an alternating series? We saw this before in 9.1, which was called an alternating sequence. But remember, a sequence has commas in between the terms. A series is we're adding up all the terms in this list. So what would this be equal to? Well, I guess we could take the first two and add them, the next set of two and add them, and then on down the line. And of course, those would all be just 0. 0 plus 0 plus 0, of course, is just equal to 0. This dot, 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 of course, is meaning we're never stopping. So maybe this is kind of leading us to this idea of an infinite series. But if we look at it this way and we take all these pairs and add them, I guess that would of course just be equal to 0. But maybe consider this. What if we didn't want to add that first term, that first blue 1 right here? What if we wanted to neglect it and then add the second and the third terms together, and then continue that pattern down the line where we did negative 1 plus 1 plus another negative 1 plus 1? In that case, we'd still end up with 0 for those, but since we left off that first one, we of course would have to add that to the result. And if we do that, we get a 1 here. So this produces a big dilemma. We of course know 0 does not equal to 1. So this problem is the inspiration for studying the studying of how to add things up infinitely often. This idea of adding up numbers forever is a kind of unintuitive thing for most people. So this kind of is the inspiration for what we're going to do here, is how do we add up an infinite amount of things? And if we do add up an infinite amount of things, is it actually possible to get a finite number? Because I think for most people, they would just assume if you add up an infinite number of things, you would of course get infinity. But maybe we'll kind of be surprised at some of the results we'll see in certain types of problems. So just some quick summation notation here, because we saw this way back in 4.2 when we did our Riemann sums. So hopefully you're okay with summation notation, but just a quick review of it. If we have this summation notation, what this is telling us to do is to start at n equals 1 here at the bottom, and to stop once we get to n equals 3 at the top. The way we do this is we start with the number that is at the bottom. Here it's a 1, so we'll plug in 1 wherever we see an n. So that'll be 1 over 1 plus 1. And then of course we'll plug in 2. So that'll be 2 over 2 plus 1. And then we'll stop once we get to this upper number, which is 3. And that'll be 3 over 3 plus 1. And again, keep in mind, this sigma, this Greek letter sigma, is summation notation, which is telling you to add each of the terms that we're getting. This is not a sequence where there was commas in between. This is now a series, which means we're adding up all the terms. Ultimately, if you add these up, you'll get a value of 23 over 12. Okay, so now let's really start digging into this idea of trying to add up an infinite amount of things. This would definitely be a video, just like many of the videos, in case I don't say it in this chapter, that you might want to rewatch a couple times just to make sure this new idea sinks in. This is definitely a very foreign idea to most of us, so some of these ideas probably will take a while to sink in. So how do we write down an infinite amount of things that we're trying to add up? Well, let's suppose we wanted to add up a bunch of terms, and in general we're just going to call that a1 plus a2 plus a3 plus a4 plus dot dot dot, meaning we're never going to stop adding these terms up. Well, we can use again our summation notation, which makes things really nice. Here we're starting at a1, which means our n begins at 1. And since we have that dot 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 at the end, that of course means we're never stopping, so we're going to have that infinity at the top of our sigma to indicate that we're never stopping. Of course, our series general term here, I'm just calling a sub n. Of course, at some point there'll be something actually there, but in general we're just going to call that a sub n. So if we wanted to write out the terms, we again would start at 1, so we'd get a1, then a2, then a3, then a4, and again, this is a series, so we're adding up all of those terms in that list. So just like you heard me say a second ago, an infinite series is just the sum of an infinite collection of terms. So to kind of build up to this idea of figuring out what something like this might be equal to, we need to talk about something called a partial sum of an infinite series. And it kind of makes sense if you just take a look at what this means. We're going to look at part. Partial, of course, just means a part. We're going to look at a part of the sum. Since we're going out to infinity, we really don't understand that. That's why we have this question here. How do we make sense of adding things up to infinity? Well, what we can do to kind of build up to that idea is look at just part of that infinite amount of stuff we're adding up. In other words, a partial sum. So we're going to solve an easier problem and hopefully make this grand problem of infinity a little bit easier to understand. And again, we're going to look at something called a partial sum, a part of these sums that we're going out to infinity. So let's start by adding a few terms at a time. The first sum I'm going to call S1. And of course, that would just be the first two terms that we're adding, a1 plus a2. And that sum, whatever it happens to be, I'm going to call the first sum, or S1. The next sum I'm going to look at is called S2. That would of course be, we would take the first sum, which is S1, and add to it the next term over. So that would mean S2 would be S1 plus A3, or if you want to write out each of those, it would be A1 plus A2 plus A3. If we wanted to look at the third sum, you can kind of see the pattern. We would take S2, which would be this piece, and add to it the next term over, which would be A4. So S3, which is the third sum, would be the first three terms plus the next term over. Ultimately, we can kind of generalize this. You can realize that the last term, you'll notice here we have a 4, here we have a 3, here we have a 3, here we have a 2, here we have a 2, here we have a 1. What you can realize is that the last term in each of these sums is one larger than the sum we're looking at. For S3, we're ending at the fourth term. For S2, we're ending at the third term. So just a little note to make, so now that we can kind of generalize this. What if I wanted to find the general sum, the general partial sum? Well, that would of course mean we'd have to take A1 plus A2 plus A3 plus A4, and since we don't know where we're stopping, we know the very last term in this partial sum would be A sub m plus 1. Again, remember, if you look at these first three sums above, wherever we're at in terms of the sum, we end at one more higher than that. So of course, if we're here at S sub m, we're going to end at A sub m plus 1, whatever term that happens to be. Of course, if this was the 10th sum, then we would end over here at the 11th sum. I'm sorry, the 11th term. So we just need to generalize that, so now that we can form this sequence. The sum of S1, S2, S3, all of those sums form a sequence. And that sequence we're of course going to denote like you saw back in 9.1. When we have these little squiggly bracket kind of things, we're saying that we have a sequence. And we're to take all these sums and list them. S1, S2, S3. We're not adding them, we're going to list them off as a sequence. Then we can of course write that in that sequence notation. And that's what we actually have here. This S sub m sequence is the sequence of partial sums for this infinite series right here. So that's kind of a lot to take in. So definitely kind of replay this if you need to kind of understand this again. But what we just did is we took our infinite series right here and we wrote it out as a sequence of partial sums. And you'll see why in a moment, but that's the goal. We wanted to take this thing that goes out to infinity, which we don't understand, and maybe write it in a sense of something we do understand, and we certainly understand sequences from 9.1. What we're doing is we're listing off all of these sums, S1, S2, S3, as a sequence. The reason we're going to do that is because of something we learned in 9.1. If we want to figure out if a sequence converges or diverges, we need to take its limit. And just like we saw in 9.1, if that limit exists, then we know that that sequence converges. If we know that we get infinity, we know that that sequence diverges. So read this very carefully here. If the limit of this sequence of partial sums exists, then what that means for the infinite series is that it can be summed up. In other words, the infinite series will also converge. So kind of let that sink in for a moment. What we're saying here is that if we take this limit of partial sums and it actually exists, then that would mean the corresponding infinite series also converges. And that's a big, big idea because we really don't, again, understand how to add up things forever. But if we approach it by looking at these partial sums and seeing if those things converge, then we can make the conclusion that that infinite series also converges. Okay, so that was definitely a lot to take in there. So again, let me reiterate, please replay this slide over again if you really are having trouble understanding how we're taking a sequence and relating it to this infinite series. And again, be careful with the words. I might even misspeak. A sequence and a series are two very different things. Of course, as a little follow-up here, it turns out, of course, if the limit of our sequence doesn't exist, then of course our infinite series diverges. So that at least is kind of easy to understand once you understand everything that we talked about before in this slide. Okay, so let's kind of take what we've seen in that last slide and see if we can apply it to this particular series right here. And you should kind of recognize the form of it in a sense. Again, remember, we're looking at series here, so this is the notation for an infinite series. And this should kind of look a little bit familiar. This piece we saw back in 9.1 as an alternating sequence. But of course, we're not dealing with an alternating sequence here. We're dealing with an alternating series. And of course, that's much different because we're taking the terms here and adding them up and not just putting commas in between them. So what does this alternating series look like when we expand it? Well, of course, if you want to expand these terms, you're just going to start with 1 and plug it in and figure out that number. Go to 2, plug it in, figure out that number, and again we're adding up all these terms. What we end up with is 1 minus 1 plus 1 minus 1, and on and on and on and on. And again, you can see why it's called an alternating, and in this case, series. So really the idea is this. If we want to determine if an infinite series converges, we need to take the limit of the sequence of partial sums. This thing right here is basically what you should have taken away from slide number 2. That's the piece of information that hopefully you're kind of conceptualizing in your head now. If we want to figure out what an infinite series is doing, we need to take a look at the sequence of partial sums. If that sequence converges, then the infinite series converges. If that sequence of partial sums diverges, then the infinite series diverges. So be very careful with these words sequences and series, because I may even misspeak when I say them. So just be very careful in the way that you're using these words. Okay, so let's go ahead and take a look at the sequence of partial sums. What is the first partial sum? Well, that would be the first two terms. 1 minus 1, which is 0. And we're again going to call that first sum little s sub 1. And I'm going to just note that that's of course an odd term, so to speak. The next partial sum would be s2. So what's that going to be equal to? Well, it'll be s1, which we got is 0, plus the next term over, which would be 1. So we'll get 1 as the result. If we want to find the third partial sum, we'll take the first 4 terms and add them up. And in this case, we'll get 0. And for one more time, because you can kind of see the pattern here, for the next partial sum, which is the fourth one, we'll take the first 5 terms and add them up, and then we get a 1. And remember, this sequence that we're forming is going to tell us something about this infinite series. We really don't understand how to figure out what this infinite series is doing unless we look at the sequence of partial sums. And once we look at that sequence, then we can maybe figure out what's going on with our infinite series. So, is this sequence approaching a particular value? Well, you'll notice we have a 0, and then we have a 1, and then we have a 0, and then we have a 1. So you can see this sequence of partial sums is alternating. So no, the limit of this sequence of partial sums does not exist. If we take the limit, you'll notice it's just alternating and not approaching a particular value, so that limit does not exist. So the conclusion we can make is that this corresponding infinite series diverges. Since the sequence of partial sums doesn't approach a particular value, then we know the corresponding infinite series must diverge. So a very important idea that we're now seeing here in this first example that we first were trying to figure out in the last slide. Bottom line is this, and I don't think you're really going to have much an appreciation for this until we kind of go into the next sections of Chapter 9, but how do we find the limit of a sequence of partial sums? This is really the only example I've done here. So in general, how are we going to do these problems? Are we always going to list off a bunch of partial sums and then see what happens? Well, the answer is no. In most cases, to figure out this sequence of partial sums, it's just way too complicated. We just, as a human race, I suppose, right now, haven't quite figured out how to do a lot of these problems. So what's going to happen is we're really not going to ever be able to determine what an infinite series sums to, assuming that it does converge. Of course, this statement right here is making the assumption that the infinite series converges. So, unfortunately, we just don't know enough about these to always figure it out. So really what it's going to come down to is we're going to only be able to determine whether the series sums to a number or not. Or bottom line is this. We're really just going to figure out with these infinite series, do they converge or diverge? That's really the bottom line. If it turns out that an infinite series converges, we probably won't know what value it converges to. Of course, if the infinite series diverges, then it's never going to approach a number, so that wouldn't matter in that case. But just kind of keep that in mind. A lot of the times we're just trying to figure out, does an infinite series just converge or diverge, and not necessarily the number that it converges to, if it happens to converge. Okay, like I said in that last slide, we aren't always going to be able to figure out what an infinite series converges to. We're just going to be able to say, does it converge or diverge? But there's one special kind of series where we can actually figure that out. And it's a series you all studied last year in pre-cal. That is something called a geometric series. So, like you see here at the top, unlike most series, if a series is geometric and it converges, we can actually figure out what it sums up to be. And we can not only just say it converges, we can actually figure out that number it converges to. But again, keep in mind, in a lot of the other infinite series we're going to look at, we're not going to know what it actually converges to. So just to make sure you can recognize when a geometric series is present, the way a geometric series looks is we have some sort of number times another number raised to the n power. In this case, we're starting at 0. We can also start at 1, but we're going to save that for a second in a moment. In general, a geometric series has this form right here. It's a number times another number to the n power. And of course, if you were to expand that, we would just have a times r to the 0 plus a times r to the 1, and so on. So, as it turns out, if the absolute value of r is less than 1, and yes, r can actually be a negative number, so basically we're saying ignore it if it's negative. If that r value is less than 1, and we're starting at 0 here, we know that that geometric series will converge. And it's going to converge to the value of a over 1 minus r. There are many, many formulas up until this point in calculus that we've had to kind of commit to memory. So I usually don't like remembering this formula as a over 1 minus r. I think a more powerful way to remember this formula is to realize that a is really the first term. You'll notice up here, r to the 0 power is really 1, so your first term is just the a. And then in the bottom, we're dividing by 1 minus r, and that r is what we call the common ratio. It's whatever is being raised to the nth power. If you kind of look at it that way with the words, I think you'll be a little more successful in kind of memorizing this formula. And honestly, we can kind of stop right here in a sense and just memorize these words to understand this formula. Because as it turns out, if n starts at 1, our formula looks a little bit different. And that's kind of why I think it's easier to remember the words instead of these formulas. If n starts at 1, our first term is going to be a times r. You'll see right here, the first term is a times r to the first power, or just ar. So in those cases where n starts at 1, you'd have to realize that the first term is ar, and luckily we're still dividing by 1 minus the common ratio. So I think it's a lot easier just to remember that the first term goes in the top of this fraction. Then you never really have to worry about the 0 and the 1, just as long as you know how to figure out what the first term is. But either way you memorize this formula, this is what a geometric series converges to. If r is ever bigger than 1 or equal to 1, Luckily, in those cases, we can just say that that geometric series diverges. Okay, so let's take a look at a few problems. I think the challenge with these problems, like many times in this course, is can you take the problem and make it look like a geometric series if it doesn't happen to look that way. Luckily here, this definitely looks like a geometric series. I see a number times another number to the nth power. What number is in front of our parentheses? Well, our a in this case is a little invisible 1 here, and then our r, which is the thing being raised to the nth power, is just 1/10. That 1/10 is definitely less than 1, so this geometric series definitely converges because of that. And if it converges, we can apply our formula here. We know that the first term here is going to be 1 times 1/10. It's going to be, since we're starting at 1 here, be careful, our first term is going to be 1 times 1/10 to the 1 power, or just 1 times 1/10. And in the bottom, we're going to divide by 1 minus the common ratio, which is again 1/10. If we perform the simple arithmetic here, we'll get 1/10 over 9/10, and when we have this fraction in the bottom, hopefully you know the quick little trick is to flip that and multiply by the reciprocal. So 1/10 times 10/9 is of course just 1/9. So this geometric series not only converges, but we can also say that it converges to 1/9. And as another reiteration of this, in other series that we're going to study later, all we're going to be able to do is maybe say that it converges. We're not going to be able to know that it actually converges to some number, like in this case, which is 1/9. Okay, so that's just kind of a little warm-up basic one. Here's an AP kind of test kind of problem. Do you recognize this as a geometric series? Well, at first glance, it definitely doesn't look like one. So we're going to have to do a little bit of algebra to make this look like the geometric series form. And again, remember, the geometric series should be a number times a number to the nth power. So how are we going to do this? Well, the first thing I'm going to do is I'm going to take that 3 out of the top of the fraction so that we can rewrite this as 1 over 2 to the nth power. Here's a trick we're going to use in this very first example and through basically the entire chapter 9 at various points. We can rewrite 1 as an n power. The reason we can rewrite 1 as 1 to the nth power is because 1 to any power is itself. So I guess the question really is, why would we want to rewrite 1 as 1 to the nth power? Well, the good news is, if you remember this back from 9.1 when I did this in one of the examples, if you ever have a division of two things that have the same power, we can kind of, for the lack of a better word, factor out that power. So really 1 to the n over 2 to the n becomes just 1/2 all to the n power, and now you can see that this is definitely a geometric series. We have a number times another number to the n power, and of course that makes our a value 3, and that makes our common ratio 1/2. Since that common ratio of r is less than 1, we know this geometric series converges. And if it converges, we can find out the value of it. So how do we find that value? Well, again, we're starting at 0 here. So what we need to do is take the first term and put that in the top of the fraction. So what would the first term be? Well, if we plug in 0 here for n, of course anything to the 0 power is 1. 1 times 3 would just be 3. So our first term, if you want to label it like we put over on the left side of this slide, our first term is 3. And then we need to divide that by 1 minus the common ratio, which is 1/2. When we do that math, we'll get 3 over 1/2. Again, we'll have to flip that bottom fraction out of there by making it a multiplication. So 3 times 2 is 6. So again, not only do we know that this geometric series converges, we can go one step further and say that it converges to the value of 6. In other series that we're going to study later on in this chapter, we might not be able to know what it converges to. We'll just be able to say whether it converges or diverges. Okay, so not to sound too repetitive here, but like you've heard me say a few times in this lesson so far, definitely stop and go back and watch some of these slides in terms of their explanations, in case these definitely foreign and new concepts are kind of not quite sinking in right away. These are definitely not intuitive ideas, so they could take some time to kind of sink in here, and that would definitely be the case with these next two slides. Luckily, the top half of this slide is pretty easy to understand. What we have going on here is just a few properties that we need to go over, and that is if we have two infinite series that are convergent, and if I tell you the A infinite series converges to some value A, and the B infinite series converges to some value B, then we can actually write out something that I think makes a little bit of sense. If we take those two infinite series and add or subtract them together, then of course their results we can add or subtract together. So a fairly kind of common sense math thing we've seen so far in calculus, so not a big deal. Same thing goes for if we multiply an infinite series by a constant, and in this case we're going to call that constant C. If we have a constant times our infinite series A, and of course we know A, the infinite series A is equal to capital A, then of course that result would just be C times A. So two little things we might use from time to time, so not a big deal. The main part that you might need to rewatch a few times before it kind of sinks in will start here and continue into the next slide, and that is the limit of that infinite series that might be converging. So what is the limit of a converging series? Well, here we have this if-then statement, and this is going to be very important in terms of the order when we're talking about an if-then statement. If you're told that an infinite series converges, then we know the limit of that infinite series must be equal to 0. That is to say, if we take this infinite series and expand it out, a1 plus a2 plus a3 plus a4 and on and on and on, we know that's going to approach a specific value because it's converging. And because of that, if we take the limit of that infinite series, that will be equal to 0. So the order of, again, this matters. If this infinite series converges, we know that the limit of that series is equal to 0. Or in other words, if the sum of this infinitely many terms is converging, then we know the terms must be shrinking down to 0, which means when we take its limit, it would be equal to 0. So I got through just saying a couple times that the order matters here, because the opposite is not correct. If you take the limit of an infinite series and get 0, then that associated series might converge or it might not. All that's going to tell you is that we can't conclude anything, and the key word is yet. We're not going to be able to conclude anything yet. The rest of the sections of this chapter, 9.3, 9.4, 9.5, and 9.6, are devoted to some techniques to figuring out if an infinite series converges or diverges, especially if it gives you 0 when you take its limit. So that's the key. The opposite isn't correct. If you take the limit of an infinite series and you get 0, all you're going to be able to say is, I don't know. And not for a while until we see some other techniques. So kind of just keep that in mind, because that's going to lead us to the first test for helping us figure out if a series, an infinite series, is converging or diverging. Okay, this is going to be the first test of several tests we're going to use to look at infinite series to determine what they are doing. This is called the nth term test for divergence. And I just want to point out, this is the key in this title. This test is not going to tell us if an infinite series converges. All it's going to tell us is if it diverges. Again, the next lessons we're going to look at, we'll take a look at some other things that'll help us tell us if an infinite series converges. So what does this test say? Well, if we take the limit of an infinite series, this a sub n right here is our infinite series, as you can see right here. If we take the limit as n goes to infinity of our infinite series and we get something that is not 0, as long as we get something that is not 0, we can say that that infinite series diverges. And that's very, very important. But just like you saw in that last slide at the bottom, be very, very careful. If you take the limit of an infinite series and get 0, all we can say is, we don't know. The test is inconclusive. There is no conclusion we can draw, from taking the limit and getting 0. We need some sort of other techniques to figure out if the series converges or not. And like I said, in these next lessons in Chapter 9, we'll start talking about those techniques. But for now, all we have is this test to see if infinite series diverges. If we get a 0 for the limit, all we say is, we don't know, and the keyword is yet. Okay, so let's kind of put this nth term test for divergence to use. We're going to try to determine whether these following infinite series converge or diverge. So here we have this infinite series, and if we want to use this nth term test, we just need to do what it says. We need to take the limit of that infinite series and see what we get. So let's go ahead and do that. A lot of these limits, at least certainly here at the beginning of these problems, should be very basic. We're going to ignore that plus 1 in the bottom since we're taking this limit to infinity. N squared over n squared is just a 1. And of course, if we take the limit of a constant, we just get that constant. But what's most important here is that we don't get a value of 0. Remember, if we get a value of 0, the test is inconclusive and we don't know what's going on. But as long as we get some number, any number, as long as it's a number other than 0, we can say that this infinite series diverges because its limit is not equal to 0. In this next example, what's going on here? Well, in certain problems, unlike this first one, we also need to be well versed in identifying geometric series. So I'm kind of spoiling the surprise here by saying that, but we don't need to take the limit of this. And as a matter of fact, we wouldn't even really know how to take the limit of this because we'd end up with like 2 to the infinity power or 3 to the infinity. And, that's not going to really help us out or make too much sense here. So what we need to do is recognize that this is actually a geometric series. Recall, we can rewrite the 1 in the top of both of these fractions as a 1 to the n power. And if we do that, since both the top and the bottom have an n for the power, we can, in a lack of a better way of saying it, factor out that power. So we have really 1/2 to the n power and 1/3 to the n power, which are both geometric series. And bottom line is, since we're just trying to figure out if these series converge or diverge, the r in the first geometric series is less than 1, which means it converges. The r in the second geometric series is less than 1, which means it converges. So of course that must mean that the overall infinite series must also converge. Of course, we could actually figure out what that number is, but we're not going to do that. We're trying to figure out, does this infinite series converge or diverge? In this next example, there's definitely no way this is a geometric series, so we're just going to go ahead and take the limit of this infinite series. So what is this limit equal to? Well, if we plug in infinity in the top and the bottom, we get infinity over infinity. And the great thing about seeing L'Hopital's rule back in Chapter 8 was that now we can actually figure out what this limit is, or we would have been stuck without L'Hopital's rule. So since we got our indeterminate form, we take the derivative of the top and take the derivative of the bottom. Since we have this fraction in the bottom of our overall fraction, we need to flip that to the top. And that, of course, would just be n over 1, or times 1, which would just be n. And of course, when we take the limit of n as n approaches infinity, we just get infinity. If we ever get anything other than 0, and especially in the case of getting infinity, we know that this infinite series diverges because the limit of it is not equal to 0. In this last example, same idea. We're trying to figure out if this infinite series converges or diverges, and the only test we have right now to figure out what's going on here is this test up at the top, the nth term test for divergence. So we're going to have to take the limit of the infinite series 1 over n squared. If we take that limit, you'll notice something. We'll get 0. 1 over infinity squared, or just 1 over infinity, would be equal to 0, and be careful here. Based on this test, and we're going to accumulate a lot more tests, but at least for right now, we can quickly see that because this limit, just like you see up here, because our limit is equal to 0, all we can say here is we don't know anything, really. Since the limit of these terms is 0, we don't know if the series converges or diverges. There's just not enough info we know, but the keyword is yet. We'll be able to figure it out this one soon enough, but for now, we're just going to say we don't know if it converges or if it diverges. Okay, in this last slide, please take note somewhere that this really isn't going to apply to the AP test. Again, I'm trying to be very thorough here in some of these lessons just to kind of give you a really good overview of a lot of the things that we're dealing with here in Chapter 9. But just take note, we've never really seen this type of special series called a telescoping series on the AP test. So just to kind of expand our knowledge here and see one other type, just kind of take in this process, but don't stress too much about what's going on here, as I don't really think we need to worry about this with regards to the AP test, but it certainly could help you on later when you see maybe some other calculus courses later. So we again want to figure out, does this series converge, and if so, what is its sum? So we have a very special series here in a sense, and like I said, this one's called a telescoping series. If we were to take this limit, by the way, like you saw on the last slide, we would get 1 over infinity, which is 0, which technically would mean we don't know what to do. But because this falls into a special sort of kind of infinite series, we actually can figure this one out. So the first kind of procedure here is to realize that because this bottom is factored, and even if it wasn't factored, we could have factored it, but since the bottom is factored, we actually know that there were 2 fractions that made up this fraction. And what we can do, like we saw back in Chapter 8, is do a partial fraction decomposition to kind of see what those 2 fractions were that added to give us this fraction right here. And you'll kind of see why in a moment, why this is going to help us figure out what's going on with this series. So just as a quick review of this partial fraction decomposition, we're going to write a over n and b over n plus 1 because those are the 2 fractions that added to give this fraction. So of course we need our common denominator, so the a fraction needs an n plus 1 in the top and the bottom, the b fraction needs an n in the top and the bottom, and you can see since all of those fractions have the same common denominator, we can cancel those out, and then we're just left with that expression. If you remember how easy it was to do this back in Chapter 8, nothing's changed here. We're going to use the Heaviside method here to quickly figure out what a and b are. If we let n equal -1, we'll get rid of the a term, which would then mean b is equal to -1. If we let n equal 0, that'll get rid of the b term, which would then mean a is equal to +1. So really the bottom line is this. We're not really considering this infinite series anymore, we're considering this infinite series. Because again, when we took the limit of that infinite series from before, it gave us 1 over infinity, which is 0, and based on our nth term test, there is no conclusion we can make. But in this particular case, since we rewrote it as this, what we can do now is take a look at its partial sum. If you remember back from the beginning of this lesson, looking at a partial sum can tell us what's going on with some infinite series, and this would be one of those cases. So what we want to do is write the expression for the sum of the first m terms. And of course, what do we mean by m terms? We just mean the first however many terms, and so we can kind of generalize it. So let's pretend we wanted to write out all the terms of this sequence up until m, which means I'm going to just list off a few and then call the last one m. So of course the first term, we're going to plug in 1. We're starting at 1 here. So if we plug in 1, we'll end up with 1 over 1 minus 1 over 2. When we plug in 2, we'll end up 1 over 2 minus 1 over 3. And I'm purposely putting parentheses around these because this would of course be the first term, this would of course be the second term, this would of course be the third term. And then we're going to put plus dot dot dot, and then plus some, I guess, I don't want to call it the last term, but it's going to be the last term because we're going to just look at this set of partial sums. The last term, which we're calling m, would be 1 over m minus 1 over m plus 1. Okay, so why did we write out this partial sum? Well, there's one thing you might be noticing here, and we're going to go ahead and start doing what you might have noticed. We can actually cancel some of these terms. We have a negative half in the first term, plus a positive half in the second term, so of course those would cancel. In the second term, we have a negative 1/3, and in the third term, we have a positive 1/3. So those would, of course, cancel. And then you can, of course, imagine, if we had kept writing this out, that negative 1/4 would have canceled with a positive 1/4 in the next term. And if we go all the way down to this last term, just imagine we wrote the term right before this last one. Based on this pattern of canceling, we would have canceled that 1 over m term with the term prior to it, which would have been some sort of negative 1 over m. So when you think about it, and now that we've expanded this out, really we're just looking at 1 minus 1 over m plus 1. And this is why we call this kind of a series a telescoping series. It kind of condenses down to be just two easy little things. All of those in-between terms end up canceling out, and that's kind of why it's called, again, a telescoping series. So can we actually figure out what's going on now based on this partial sum? And the answer is yes. Remember, from what you saw at the very beginning of this lesson, since that's our partial sum, we're not going to infinity here, that's just our partial sum. If we look at the limit of the partial sum, that will tell us what the original infinite series is doing. So let's go ahead and take the limit of that partial sum. If we take this limit as m goes to infinity, we'll get 1 over infinity plus 1, which is really 1 over infinity, which is 0. And of course, the limit of 1 is just 1. If the limit of our partial sum gives us a finite number, then we know that our corresponding infinite series converges. And that's the key. Since the limit of the partial sum is 1, we know that the series converges. So again, just take note that I don't really think you have to worry about this with regard to an AP test kind of question, but it's definitely a good way to kind of round out this whole idea of partial sums and how those relate to a converging or a diverging infinite series.